Chapter 9. Fundamental of Engine Operation. After studying this chapter, you should be able to explain the combustion process in the engine, describe how pollutants form in the engine, list and explain the two rules relating pressure and temperature, explain the difference between a thermometer and a thermostat, describe how each works, describe how temperature, humidity, and atmospheric pressure affect combustion. From atoms to power. Chapter 9 to 1. Atoms. Atoms are the basic building blocks of the world. They are very small. A single drop of water contains about 100 billion atoms. There are about 100 varieties of atoms. Each has a special name: gold, silver, iron, aluminum, oxygen, hydrogen, nitrogen, and so on. The copper or other metals in a penny are made up of billions of one kind of atom. Any substance made of only one kind of atom is an element. Chapter 9 to the 2. Chemical reactions. Atoms of different elements can connect with each other. The process is a chemical action or reaction. Chemical reactions go on around us all the time. The burning of fuel, gasoline, in an automobile engine is a chemical reaction. This reaction is called combustion. Chapter 9 to 3. Combustion in the engine. Automotive fuels such as gasoline are made mostly of two elements: hydrogen and carbon. They have the chemical symbols H and C. This type of fuel is a hydrocarbon, HC fuel. During complete combustion in the engine, these two elements unite with a third element, the gas oxygen, O. Oxygen, usually in the form of free oxygen, O2, makes up about 20% of the Earth's atmosphere. This is the air we breathe. During combustion, each oxygen atom unites with two hydrogen atoms. Figure 9 to 1. Each carbon atom unites with two oxygen atoms. Oxygen uniting with hydrogen produces H0, or water. Carbon uniting with oxygen produces CO, or the gas carbon dioxide. Dioxide because there are two oxygen atoms to each carbon atom. During combustion of the fuel, the burning gases get very hot. Their temperature may go as high as 6,000 degrees in Fahrenheit, or 3,316 degrees Celsius. This high temperature produces pressure in the engine that makes it run and produce power. With perfect combustion, all the hydrogen and all the carbon in the gasoline would unite with oxygen. The exhaust gas would contain only harmless H, water, and CO, carbon dioxide. But combustion is not perfect in the engine. Some of the gasoline, HC, does not burn. Also, some only partly burns. This produces carbon monoxide, CO. Monoxide because there is only one oxygen atom for each carbon atom. The unburned gasoline, HC, and partly burned gasoline, CO, exit from the engine through the tailpipe. Once in the air, they cause atmospheric pollution. Another group of atmospheric pollutants from the engine is nitrogen oxides. No. About 80% of the atmosphere is the gas nitrogen, N. The high temperatures in the engine cause some of the nitrogen to unite with oxygen. This forms the nitrogen oxides. Automobiles have anti-pollution devices called emission controls. These reduce the amount of the pollutants, HC, CO, and NO. Chapters 35 and 36 describe emission controls and their service. Chapter 9 to 4. Essentials for engine. The automobile engine has 3 or more cylinders. A piston moves up and down in each cylinder. Figure 9 to 2. Figure 9 to 3 shows the piston and cylinder in a 4-cylinder engine. The car moves because the pistons move. Before the pistons move up and down, the engine must have fuel available. Gravity, atmospheric pressure, and vacuum make it possible for the fuel to get into the engine cylinders. There, the fuel burns to produce power. Chapter 9, 5. Gravity. Gravity is the attractive force between the Earth and all other objects. When you release a stone from your hand, the stone falls downward. When you drive a car up a hill, part of the engine power is used to raise the car against gravity. A car coasts down a hill with the engine not running and the brakes off. Gravity pulls the car downward. Chapter 9 to 6. Atmospheric pressure. Gravity also pulls the air toward the Earth. At sea level and average temperature, a cubic foot of air weighs about 0.08 pound, or about 1.25 ounces, 0.035 kilograms. This is very little, but the blanket of air, our atmosphere, is many miles thick. It is like many thousands of cubic feet of air, stacked one on top of another, all adding their weight, figure 9:4. The total weight or downward push of all this air is about 15 pounds per square inch, psi, 103 kPa. This is at sea level. The human body has a total surface area of several square feet, or several hundred square inches. The total weight of the air on your skin amounts to several tons. This pressure does not crush you, because pressures inside you balance these outside pressures. Chapter 9-7. Vacuum. A vacuum is the absence of air. When a piston moves down in a cylinder, figure 9:2, the piston creates a partial vacuum. Atmospheric pressure then pushes air into this. Chapter 9-8. The engine cylinder. The same actions take place in all cylinders. Figure 9-5 shows one cylinder of an engine. The piston slides up and down in the cylinder. Figure 9:2. There are at least two openings or valve ports at the top of the cylinder. Valve ports are internal passages in the cylinder head. This is the engine part that encloses the top of the cylinder. There is a valve centered in each port. A valve is a device that can be opened and closed to control the flow of a liquid or gas. The engine valve is a plug with a round head on a long stem. Figure 9-6. It is moved up and down at the proper time by the valve train, as explained in Chap. 14. This closes the port so no air-fuel mixture or exhaust gas can enter or leave the cylinder. Two valves are shown in figure 9-7. One is the intake valve. When it is down or open, figure 9-7a, air-fuel mixture can flow into the cylinder. The other valve is the exhaust valve. When it is down or open, figure 9-7d, the burned gases remaining from combustion, 9-3, can flow out of or exhaust from the cylinder. Chapter 9-9. Actions in the engine. Figure 9-7 shows what happens in one cylinder when the piston moves up and down, and the valves open and close. In figure 9-7a, the piston is moving down and the intake valve is open. Figure 9-7 shows what happens in one cylinder when the piston moves up and down, and the valves open and close. In figure 9-7a, the piston is moving down and the intake valve is open. Atmospheric pressure pushes air past the open intake valve and into the engine cylinder where there is a partial vacuum. On the way, the fuel system mixes fuel vapor with the air. The intake valve closes after the piston passes its bottom position and starts to move up again. Figure 9-7b. The bottom position is called bottom dead center, or BDC. As the piston moves up, figure 9-7b, it compresses the air-fuel mixture into a small space called the combustion. Figure 9-7 shows what happens in one cylinder when the piston moves up and down, and the valves open and close. In figure 9-7a, the piston is moving down and the intake valve is open. Atmospheric pressure pushes air past the open intake valve and into the engine cylinder where there is a partial vacuum. On the way, the fuel system mixes fuel vapor with the air. The intake valve closes after the piston passes its bottom position and starts to move up again. Figure 9-7b. The bottom position is called bottom dead center, or BDC. As the piston moves up, figure 9-7b, it compresses the air-fuel mixture into a small space called the combustion chamber. Then, as the piston nears its top position, called top dead center or TDC, the spark plug fires. The spark plug has an air gap of about 0.040 inch, 1 mm. The ignition system produces and delivers a spark that jumps this gap at the right time. Chapter 31 and 32. The spark sets fire to or ignites the compressed air-fuel mixture. Figure 9-TC. The temperature of the burning air-fuel mixture goes up as high as 6,000 degrees, 33 degrees. The result is a high pressure in the cylinder, which can be as much as 600 psi, 140 pa. The pressure pushes down on the piston with a force of up to 4,000 pounds, 17,792 newtons, N. This pushes the piston down. The downward movement, carried through the connecting rod, rotates the crankshaft. It turns gears and shafts to move the car. Chapter 11 describes this series of actions. As the piston approaches BDC, the exhaust valve moves down. This opens the exhaust port. When the piston moves through BDC and starts upward, the burned gases leave the cylinder. Figure 9 to 7D. They enter the exhaust port and pass through then tailpipe into the atmosphere. Basic physics. Chapter 9 to 10. Expansion of solids. Understanding engine operation requires knowing some basic physics and chemistry. They help explain how increasing temperature of the burning air-fuel mixture produces high pressure, and this high pressure produces piston movement. One fundamental is the expansion of solids with heat. Any solid, such as the metal in an engine piston, expands and gets larger when its temperature goes up. However, the piston must be free to move up and down in the cylinder, even if it gets very hot. Figure 9.8. A piston that expands too much will stick in the cylinder. This damages the engine. The piston is designed to expand very little as it gets hot. Chapter 9 to 11. Expansion of fluids. With heat, fluids are substances that can flow. Examples are water and air. Both expand when heated. 1 cubic foot of water, 0.0283 cubic meter. At 32 degrees, 0 degrees C becomes 1.01 cubic foot, 0.0286 cubic meter. When heated to 100 degrees, 37.8, 1 cubic foot of air, 0.0283 cubic meter, expands to 1.14 cubic foot, 103.3 cubic meter. When heated to 100 degrees, 37.8 degrees C. This occurs without a change of pressure. Chapter 9 to 12. Increase of pressure. With temperature, something different happens. When air is heated in a closed container, that will not allow the air to expand. Heating a cubic foot of air from 32 degrees to 100 degrees, from 0 to 37.8 degrees, increases its pressure about 10%. This means a beginning pressure of 15 psi. 103 kPa will increase to a pressure of 17 psi. 117 kPa as the air beats up. This is the first rule. Pressure increases with increasing temperature. Chapter 9 to 13. Increase of temperature. When the piston moves up in a cylinder, figure 9 to 7b, or closed container, the piston compresses the trapped air or air-fuel mixture. Then the air or mixture gets hot. This is the second rule. Temperature increases with increasing pressure. Both rules are at work in the engine cylinders. Compressing the mixture, increasing its pressure, increases its temperature. Igniting and burning the mixture raises its temperature still further. This further increases its pressure. Increasing the temperature increases the pressure. This high pressure then pushes the piston down, which moves the car. Chapter 9 to 14. The thermometer. The thermometer, figure 9 to 9, is a hollow tube partly filled with a liquid such as mercury. The liquid expands as its temperature increases. This forces some of the liquid to move up in the hollow tube. The higher the temperature, the more the liquid expands, and the farther up it rises in the tube. Degree marks on the tube indicate the temperature. Chapter 9. 15. The thermostat. Different metals expand different amounts when heated. For example, aluminum expands about twice as much as iron. One type of thermostat uses this difference in expansion of metals. The coil thermostat, figure 9 to 10, is made of two different metals, such as brass and steel, welded together. Heating the coil makes one metal expand more than the other. This causes the coil to wind or unwind. The motion of the coil then controls the flow of a fluid or electricity. Chapter 9 to 16. Producing a vacuum. A vacuum is an absence of air in Chapter 9.7. The engine produces vacuum as the piston moves down during the intake stroke. Figure 9 to 7a. This is how a vacuum pump produces vacuum. Other devices produce vacuum or operate by it. To control or use the vacuum, sometimes we need to know how strong it is. The barometer and vacuum gauge provide this information. They read vacuum. 1. Barometer. The barometer uses vacuum to measure atmospheric pressure. You can make a barometer by filling a long tube with mercury, figure 911, then cover the end to seal it closed. Turn the tube upside down and put the end into a dish of mercury. HA. Now remove the seal to open the end. Any increase in atmospheric pressure acts on the mercury in the dish. This forces some of the mercury up the tube. Any decrease in atmospheric pressure allows some of the mercury to flow out of the tube. If this happens, the barometer is falling. It usually indicates stormy weather. 2. Vacuum gauge. The vacuum gauge, figure 9 to 12, is a type of pressure gauge. It measures the pressure in a closed space and compares it with atmospheric pressure. A partial vacuum exists if the pressure in the closed space is less than atmospheric pressure. The vacuum gauge, chapter 5 to 22, reads in inches of mercury. However, there is no mercury in the gauge. When connected to a running engine, the vacuum gauge shows how much vacuum the engine is developing. This is an indication of engine condition. For example, a low or unsteady reading indicates engine trouble. A later chapter describes using the vacuum gauge in engine diagnosis. The vacuum gauge has a bellows or diaphragm linked to a needle on the dial face. Applying a vacuum moves the bellows or diaphragm. This causes the needle to move to show the amount of vacuum. Instead of a needle and dial face, some vacuum gauges have a digital display. Many vacuum gauges have a small chamber with a nearly perfect vacuum. The gauge compares its reading with this vacuum to get absolute vacuum. Chapter 9 to 17. Humidity. Most air has some water vapor, evaporated water, in it. When the air is carrying a lot of water vapor, the air is humid. Air around bodies of water has high humidity. Air over deserts has low humidity. Humidity is measured as a percentage. 0% humidity means the air has no water vapor. 100% humidity means the air is holding all the water vapor it can hold. A reading of 50% humidity means the air is holding half as much water vapor as it could. Humidity affects engine performance. An engine develops less power in hot, dry air than in cool, moist air. The cool air is denser. Atoms are closer together, so more air enters the engine. This means more power. The moisture displaces some of the oxygen from the air. This richens the air-fuel mixture. Then the engine runs more smoothly. Chapter 9, 18. Atmospheric conditions affecting combustion. Changes in temperature, humidity, and atmospheric pressure affect combustion in the engine. They change the way the fuel burns and the amount of power the engine produces. Chapter 19 describes how air pressure and temperatures are measured. Proper engine operation depends on the engine computer, continuously receiving this information. Chapter 9, 19. Electricity for engines. Engines need electricity for starting and running. Chapter 1 to 18. An electric current cranks the engine to start it. Electric current also provides the sparks at the spark plugs, chapter 9 to 9, and may operate the fuel system. In addition, electricity operates the electronic engine control system on modern engines. Therefore, an understanding of how engines operate and are controlled requires a basic knowledge of electricity. Chapter 10 explains basic electricity, electronics, and engine controls. Trade talk. Atmospheric pollution, atmospheric pressure, bottom dead center, BDC, chemical reaction, combustion, element, gravity, pressure, and on top dead center, TDC, vacuum, multiple choice test. Select the one correct, best, or most probable answer to each question. You can find the answers in the section indicated at the end of each question. 1. During combustion of gasoline in the engine, 79.3. A. Oxygen unites with carbon to form carbon dioxide. B. Hydrogen unites with oxygen to form water. C. Some carbon unites with oxygen to form carbon monoxide. D. All of the above. 2. Which of these statements about a closed container is correct? 9 to 12 and 9 to 13. A. Temperature increases with increasing pressure. Odd pressure increases with increasing temperature. C. Both A and B. D. Neither A nor B. 3. Pollutants produced by the engine include 9 to 3 are water, carbon dioxide, carbon monoxide, and NO, carbon monoxide, carbon dioxide, HC, and NO, C, carbon monoxide, HC, and NO, D, water, HC, and NO. 4. Atmospheric pressure is produced by 9 to 6. B. Carbon monoxide, carbon dioxide, HC, and NO. C. Carbon monoxide, HC, and NO. D. Water, HC, and NO. 4. Atmospheric pressure is produced by 9 to 6. A. Vacuum. B. Gravity. C. Humidity. D. Temperatur. 5. During burning of the air-fuel mixture in the cylinder, the force pushing the piston down may be as high as 9. C. Both A and B. D. Neither A nor B. 3. Pollutants produced by the engine include 9 to 3 are water, carbon dioxide, carbon monoxide, and NO. B. Carbon monoxide, carbon dioxide, HC, and NO. C. Carbon monoxide, HC, and NO. D. Water, HC, and NO. 4. Atmospheric pressure is produced by 9 to 6. A. Vacuum. B. Gravity. C. Humidity. D. Temperatur. 5. During burning of the air-fuel mixture in the cylinder, the force pushing the piston down may be as high as 9. A. 600 tons. B. 600 pesi. C. 4,000 pounds. D. 1814 pounds. 6. As the piston moves up the cylinder, the air-fuel mixture is compressed and the Daumard 913. A. Temperature increases. B. Pressure increases. C. Air-fuel mixture gets hot. D. All of the above. 7. The device that provides control based on temperature changes is the 9 to 15. A. Thermometer. B. Thermostat. C. Vacuum gauge. D. Pressure gauge. 8. The atmosphere is 9 to 3. A. 80% O and 20% N. B. 20% O and 80% N. C. 20% O and 80% HC. D. 20% N and 80% HC. 9. The vacuum gauge compares a vacuum source with 9 to 16. 4. The atmospheric pressure. B. A nearly perfect vacuum. C. Either A or B. D. Neither A nor B. 10. An engine develops more power when the air is 9 to 17. A. Hot and dry. K. Hot and moist. C. Cool and dry. Is cool and moist. Review questions. 1. How are CO and CO formed in the engine cylinders? These 3. 2. How does gravity help the engine run? 9.5 and 9.6. 3. Explain what pushes the piston down. 9. 4. What are the 2 rules relating temperature and pressure? 9.12 and 9.13. 5. Explain how barometric pressure is measured. 9 through 16.